Hello, I'm Yao Xiao from Sun Yat-sen University, and I'm glad to present our paper, Max Images are Counterfactual Samples for Robust Fine-Tuning. Recently, large pre-trained models like CLIP exhibit strong robustness to distribution shift, showing significantly better performance on OD data. However, it is found that fine-tuning these pre-trained models can reduce the robustness, leading to a trade-off between ID and OD performance. In this paper, we study this issue from a causal perspective, and here is our structured causal model. We argue that fine-tuned models tend to learn the spurious correlation between symmetric and non-symmetric factors, which can be unstable under distribution shifts. Therefore, we propose to use max images as counterfactual training samples that break the spurious correlations. By applying distillation based on the max images, we can effectively improve the robustness of the fine-tuned models. Now let's drill down to the details. Thanks to the pre-training on massive data of various domains, the large pre-trained models are expected to learn the correct attribution of image semantics S to the semantic representations HS. However, due to the spurious correlation in downstream data, fine-tuned models tend to rely on both HS and HD for the prediction of S. Unfortunately, the correlation between HD and S is unstable under distribution shift. For example, while the red admiral butterflies may all be captured sitting on flowers in training data, they can appear anywhere in text images. Hence, we would like to break the learning of such spurious correlations by using counterfactual samples. To this end, we propose an intuitive method for constructing counterfactual samples. We use Clark's activation method to divide the patches of an image into context and object. Then, either the context or the object is maxed, resulting in the modification of HD or HS. It should be noted that this masking-based method is not the only way to build the counterfactual samples, and we do not expect it to cover all the spurious correlations. Based on the counterfactual samples, we apply a simple feature-based distillation method to constrain the fine-tuning, taking the pre-trained model as a teacher model. Here, the pre-trained and fine-tuning models are fed with the same counterfactual samples, and the label Y is only used for the learning of the factual sample X. By requesting consistent prediction with the pre-trained model on the semantics of counterfactual samples, we hinder the fine-tuning model from attributing semantics X to HD. Moreover, since the counterfactual samples are used for the distillation, we need to enlarge the disagreement between the fine-tuning and pre-trained model, so that the distillation loss can more effectively constrain the fine-tuning. Hence, we propose to further refill the masked regions with patches taken from other images. Specifically, context mask may not produce contradictions in predictions, since both models can predict the semantic label cat from the object patches. So we need refilling to bring some conflicting context that disturbs the prediction of the fine-tuning model. In the other case, object mask alone can produce contradictions in theory, as the fine-tuning model could still predict the cat from the context, while the pre-trained model could not. In practice, however, due to the imperfect masking, the pre-trained model may still recognize the object from its unmasked parts. So in this case, we need refilling to further distort the original semantics to enlarge the disagreement. To validate the effectiveness of the proposed masking and refilling, we conduct experiments on fine-tuning CLIP to the ImageNet classification task. Here is the comparison of different combination of strategies with different hyperparameters. The major conclusion is that both masking and refilling are important for our method. Besides, object mask is more effective than context mask, which may be explained by the less dependency on refilling. We also compare our method with existing methods for robust fine-tuning. These results suggest that our method can achieve superior OOD performance on average without using model ensemble as in WISE-FT or uniform soup. As expected, our method is particularly effective on ObjectNet and ImageNet A, where many objects are shown in unusual contexts. We further discussed the integration with WISE-FT, a weight space ensemble method. It was found that the weight space linear interpolation between the zero-shot and vanilla fine-tuned model can produce such a curve that if we take a median value of the mixing coefficient alpha, like 0.5, the ensemble model can achieve better performance on both ID and OOD data. Nonetheless, as shown by the blue curve on the right, applying WISE-FT on our fine-tuned model seems less meaningful. This possibly suggests that our model is significantly different from a vanilla fine-tuned model in terms of the loss landscape. Besides, we consider WISE-KD, which takes the WISE-FT model as a teacher to further constrain the fine-tuning. This can bring slight improvement to our method. To conclude, we argue that the robust degradation in fine-tuning can be attributed to the spurious correlation in downstream data. Then, we show that masked images can be effective counterfactual samples for breaking the spurious correlation and improving their robustness. In addition, our results suggest that the common weight space constraints may be unnecessary for maintaining the robustness. So there is still a lot of room for exploration on better fine-tuning methods. For more details, please check out our paper or the code. Thanks for watching.